Okay. All right. So exponential functions. What we're going to be talking about. Exponential. What does that mean? Exponents, right? So when we're thinking about numbers in this particular section or the next couple of sections, we're going to be thinking exponentially. Don't think in terms of what multiplies would be this. Think about what would, like the number 16. Don't think of that as 8 times 2. Think about that as being 2 to the 4th power. That kind of idea. So when we think about exponentials, think about numbers with a base and an exponent when we talk about things in this section. So if you can just kind of get your mind in that mode, that'll help. The standard form for an exponential function is f of x is equal to c times a to the x being our variable, and it's in the exponent area. The c that's in the front there is what's called the initial value. A, that's the base of the exponential there, is the growth or decay factor. Growth or decay factor is what that's called. Okay. Depending on the value of A, decides if it's exponential growth or exponential decay. So if it's growth, we're looking at A being greater than 1. Decay, A is between 0 and 1. So what kind of numbers are between 0 and 1? Decimals and small fractions. Right. So anything bigger than 1, like an improper fraction, could be there even, or a whole number. That's going to be a growth, exponential growth, and anything with a small fraction in there, like 1/2, 1/3, 0.72, anything like that, that's an exponential decay out of that. So knowing those things, kind of helpful. All right, so what we're going to do is it's going to kind of flow a little bit like those sections in chapter 4 where we talked about linear equations and quadratics, and how do you tell if a set of ordered pairs is one of those. So the first thing we're going to talk about is the set of ordered pairs exponential? If so, write the exponential equation. I'm going to use a table for the first one here. 0, 5, 1, 10, 2, 20, 3, 40, 4, 80. Some ordered pairs there. Now, if this were linear, what would we be looking for? No, that's for functions. To be a linear set of ordered pairs, what has to happen? What do linear equations have? They have slope, right? So to check if it was linear, we would find the slope between a couple of different sets of ordered pairs. If it's linear, what should the slope be for two different sets of ordered pairs? Should be the same, right? Okay, so if I did that with this, 10 minus 5 is 5, 1 minus 0 is 1, so that's 5 over 1. But if I go to this ordered pair, 40 minus 20 is 20, 3 minus 2 is 1, that's not 5, so that's not linear. Okay, we could tell that that's not linear. If it's quadratic, what kind of things do we look for? Some repeating y values, because quadratics either make the U shape opening up or opening down. Usually it's a symmetric kind of setup on our ordered pairs. You would have a vertex in the middle and then ordered pairs on either side of that. So linear slopes are the same. Quadratic kind of makes that U shape. If you were to plot these on a coordinate plane or do a scatter plot with that, you can tell. But exponentials have what's called a common ratio. Okay, so the ratio of the y values, 10 over 5 is 2, right? What's 20 over 10? What's 40 over 20? Notice it's the same every time. It's 2. That 2 that keeps happening there is the growth factor. Okay. So that because that's consistent, the ratio of our y values is consistently 2. That tells us this is exponential. If you plotted this on a coordinate plane, and I'm just going to sketch it here, we we know that this would cross the x-axis at 5, and then at 1 it's 10, 20. It kind of does this kind of number. That's what the graph looks like. It's pretty flat, and then it shoots up to infinity there pretty fast. As x gets bigger, the y's get really big fast. And we went from 0 was at 5, at 4 we're already at 80. So at 5 we would, if we follow this, we'd be at 160 at 5. We follow the same pattern going on there. So that's what's going on there. Let's write the equation for this. So this is not too difficult. So we're going to start out with the standard form for an exponential. We know the growth factor now because we looked at that ratio every single time. That ratio is 2. So that's going to go in the place of A. So it's 2 to the x. Now we got to find out what C is. C is the initial value. Okay. If you have an ordered pair in your set that has a 0 as the x, then that makes whatever the y value there be C. Why? Well, the reason that it does is because you plug in that ordered pair. Y is 5, x is 0. What's 2 to the 0 power? 1, right? So C times 1 is equal to 5. If I divide by 1, there's our C equals 5. So the final exponential function would be 5 times 2 to the x. If you don't have an ordered pair with a 0 on the x value, you can use any of them to get there. If I had used 110 and plugged it in for x and y, I'd have had 2 to the first power. C times 2 to the first power is equal to 10. Divide by 2, and C is still 5. No matter what you do there, it's always just easier when there's a 0, and what would be a y-intercept there. C is usually your y-intercept. Okay, let's look at another set. -1, 32, 1, 8, 2, 4, 3, 2. So you got to be a little bit careful here. Look at your x values. -1 to 1, 1 to 2, 2 to 3. What's going on with the x values? Yeah, you're missing the one in the middle there, that 0 between the -1 and the +1. So when we look at our ratio, we don't need to look at that ratio because we're missing an x value. We need to look at the ones that are consecutive. So 1 and 2, and then 2 and 3. So we only got 2 that we can check here. So I'm going to do the ratio. It's always the second one over the previous one. Okay. So 4 over 8 is 1/2. 2 over 4, 1/2. That's consistent with that being a what kind of factor? Is that a growth factor or decay factor? Decay. So on the coordinate plane, what's happening when you graph that is that it's getting smaller and smaller as x gets bigger and bigger, right? So the next ordered pair we would know would be 4 what? 4, 1, yeah, half of the previous y value out of that. So let's write our equation. F of x is equal to c times a to the x. We know a is a half. So we're going to find c. We don't have that ordered pair with the 0 in it. So I'm going to pick a different ordered pair. Doesn't matter which one. I'm going to pick 1, 8 because that's easy to do. It's easy to raise 1/2 to the first power, right? One half to the first power would be 1/2. Then I divide by half or multiply by the reciprocal. C is 16, should be anyway. Does that make sense that 0, 16 would fit into that ordered pair set? Yeah, because we're going 2 is half of 4, 4 is half of 8, 8 is half of 16, and 16 is half of 32. It follows that pattern that's going on there, so it makes it not too difficult there. So really simple idea here, but make sure when you're looking at your ordered pair sets that when you look for that common ratio, the growth factor or decay factor, look at your x values and make sure you're using the consecutive ones. If it skips one in between, then you don't need to use that pair of them to find that. Okay. All right. So pretty easy start. Let's get into transformations. So we've been talking about transformations since chapter 3. And we'll just do a basic one. Describe the transformation on 2 to the x. So the first one we're going to do is f of x is equal to 2 to the x plus 4. What transformation happened to? This is our original graph. What did this do to that original graph? Up 4. So it was a shift up 4 units. Those same rules that we've been using all semester still in play here. What does that do? Right or left? Right. 4 units. Anything that happens on the outside is vertical. That's where the plus 4 over here is. Inside is with the x. That's a horizontal move. Minus is to the right, plus is to the left. Who knows here? Two to the negative x minus 5. Still go down 5, but what else does it do? Yeah, reflect across the y-axis. No matter what kind of function we're dealing with, those transformations are always the same. Be mindful of those. Go back and review those out of chapter 3 if you need to. Okay. All right. Pretty easy stuff. Okay. Now let's get into my favorite part of this section, which is actually solving equations. I like solving equations because I get answers, and I can check answers to make sure they're right. Okay, so let's solve some equations. Solving exponential equations. Now we'll start with a pretty easy one. 2 to the x plus 5 is equal to 2 to the 8th. So exponential equation, the variable is going to be in the exponent. That's the nature of those. The key that we're going to try to do in this section is try to get the bases the same. And what part of that equation is the base? The 2. On each side, try to get the base to be a 2. If you can get the bases the same, then logically it makes sense that if 2 to the x plus 5 is equal to 2 to the 8th, then x plus 5 has got to be equal to what? 8. So that's the equation you're going to work. Track 5. Boom. All day? I can do that. It's as easy as Velcro shoes, man. Of course you do. That's not the same, man. You know it couldn't stay that easy, right? All right, so 16 is really 2 to the 4th power, right? So we're thinking exponentially, rewriting the number with that same base. Since 2 is the prime number there, that's how we know to try to get 16 down to 2 to a power. If you're rusty on thinking about your 2 to a powers, think factor tree. And that's 1, 2, 3, 4. So that's how it's 2 to the 4th. It's 2 to the x plus 1 equals 2 to the 4th. And so our equation that we set up to work is, yeah, and x would equal 3 again. No, he just did them last semester, so. Oh, we did? He said we did? Oh, God. All right. Let's do another. 3 to the 5x. Oh, geez, he changed the base. Is equal to 81. 81 is 3 to the 4th power. It's true. How do you make that happen? I know 81 is really 9 times 9, right? And then 3 and 3. 3 and 3. So that's 1, 2, 3, 4. 3 to the 4th power. And then how do you get x by itself? Divide everybody by 5. Boom. I do too. See, I told you it's my favorite part. Yeah. No.
4 to the 1/2.
No. 4 to the 1/2 is 2. Not 8.
Okay, wait.
Oh, that's a good idea. What base would we go for? 2, because exponentially 4 is 2 squared, right? And 8 is 2 to the 3rd power cubed, yeah. So this is 2 squared to the 2x minus 1 and 2 to the 3rd. What is the rule for those two exponents right there? You multiply them. That's exactly right. You got to know our exponent rules. So that's 2 to the 4x minus 2 is equal to 2 to the 3rd. And what is our equation we work? Add 2. 4x is equal to 5. Divide by 4. 5 over 4. Oh, that wasn't hard. Questions so far? I don't want to leave anybody behind. Yeah, sure.
I feel like you're about to throw in a quadratic exponent.
Not yet.
Wait, hang on, wait a second. Did you say not yet?
Maybe.
We're going to find all this.
3 cubed.
All right. So what does this become? 4x. Yeah, 3 to the 4x to the 3 cubed. What's our equation that we solve? Divide by 4. Let's humble you a little bit then. Oh, heck, you put a fraction in there.
1/3. 3 to the 1/3. Is that right?
All right, so we got to think exponentially here. This problem, I put them beside each other because they're very much related.
Can it make 3 to the negative one?
Does that make fractions? Oh, okay.
And that would be 3 squared.
Ah, so this is 3 squared. And then you said this is 3 to the negative 3. Because remember, a negative exponent, to make it a positive exponent, moves to the denominator. And so anytime we got a fraction there, we got to think, oh, I can kind of fix that a little bit. And then that's going to give us 3 to the 10x. So questions about that one? Fraction, if you see a fraction in the problem, you got to think negative exponents. That's just the rule, okay? Fractions in the problem, think negative exponents. So that's I. Two.
That's what we're using. 2 squared.
Okay, so 4 is 2 squared. Random math Tourette's. 2. Negative 85. All right. So what's the rule here? Multiply, right? So that's 6x squared there. So 2 to the 6x squared is equal to 2 to the 3x. What's our equation we set up? Okay, so that's quadratic. Oh man, we got to know how to do stuff that we've done before. Son of a gun. Why? Get it equal to 0, so that opens up all the possibilities for solving quadratics, which are factoring and quadratic formula. You could complete the square if you wanted to, but nobody does that. So get it equal to 0, so we're going to subtract 3x. And 6x squared minus 3x is equal to 0. GCF of 3x, good job. 2x minus 1. So 3x equal to 0, 2x minus 1 equals 0. And so that's going to be x equals 0, positive 1/2. You guys are better at quadratics than you ever were. Or should be, anyway. We've done a bunch of them.
Are we ever going to have like stuff
Next section. K. All right, let's make it cool here. E to the 2x equals e to the x minus 1. E is a number. It's kind of like pi, it just represents about like 2.71, something like that. But does it even matter for this problem? No, because the base is the same on both sides. So that's all that matters, is that the base is the same. And then we can set up the equation, 2x equals x minus 1. X equals -1. Oh, I'm done. That was nice. All right. Go out with a bang here. All right, so that's a multiplication sign between those.
You have to add the exponent.
Why?
Because when you multiply, you add.
Multiplying, you add exponents, okay? So this is e to the,
Or well,
descending order would be nice. And now? So x squared plus 7x is equal to -12. And you bring that old 12 over. And you choose your method. I'm going to factor 3 and 4. X equals -3, x equals -4. I remember doing these in Algebra 2. We did them a little bit.
You sure? I don't think we ever got.
Yeah, we did. No, it was closer to, well, midway through, but it was closer to the end because we started a month late. Yeah. Yeah, in half of the midway. Yeah. That's about as tough as they get there. Hey,
What happens if the x is canceled?
then there could be no solution, just like any other equation. If all that, it's possible. Aiden asked a good question. What if the x's all cancel out when you set that up? It's possible that an equation has no solution, right? It's also possible that an equation has all real numbers as a solution. It's just once you get the exponential part done and you set up this equation, it's back to the same rules of any regular equation as far as solving goes. All of those things could happen with that. So it's not, once you get to the equation solving part, it's nothing new. The exponential thing is what you got to pay attention to there. But that's probably about as hard as they get as far as this section goes. Pretty neat thing, though. All right. So it's 431. Dang. What's a hashtag? What? All right. Page 431. 3 through 59, 61 through 84, and then 101 through 107. So you got to do all of those, but definitely make sure you're experienced before our quiz. If you got questions, I'd start working on it today because you're going to need to know several different things there. I've got some paper towels over here, Ted, if you need those.